Welcome back. This is Dr. Hammond for Phys 2500 Intermediate Mechanics at the University of Windsor. So by now we've gone over the slides of how to set up these second order differential equations and how to solve them, and I've talked to you about second order ODE solvers with conservative systems. Now I'm going to talk about second order differential equations that are non-conservative, so some kind of drag coefficient. Or it doesn't even need to be non-conservative, just it has a velocity-dependent force. Okay, this one will be an underdamped or a damped harmonic oscillator system, as we just saw in the intermediate or in the midterm 2 question 2 for a building undergoing an earthquake. I suggest that you read this preamble so that you can see what we're trying to solve here, but I think I'll also go through this in the slides. So again, you need to import these libraries. I think we've gone over this enough. I'm going to set this up so that it's similar to how the exam was, that you have some initial velocity and there's the initial position this building is standing upright. And we'll have some natural frequency of, say, 10, and we'll have a damping factor that's, fairly small, so just 1. We'll do 500 time steps for our integration. We'll be integrating over 5 seconds, and again, dt is defined as the first time step minus the 0th time step. Okay, so now we have our second order velocity dependent ordinary differential equation, and so our derivative of our velocity with respect to time, so v dot, is going to be both a function of v and x, and so we need to return this differential equation, so minus 2 times c times v minus omega naught squared times x. And so this is just the differential equation as we saw before in the slides. So we can solve this using the midpoint integration method. And so just like what we had before, we're solving for velocity. So the next time step for the velocity depends on the current time step of the velocity plus this time step dt. And then we'll be putting in for the midpoint method, we have the current velocity plus 1/2 dt of the current velocity and current position, and then also the current position. So this is just like what we saw before for the midpoint method, but we want to integrate this twice because this is also dependent on x, and so we need to know what x is at that time. So x at the next time step depends on what the current time step of x is, plus dt. And then this looks like the Euler integration routine that you would say the current or the next position step is dependent on the current position step plus dt times v. But instead, what we'll be saying is it's dt of the next velocity instead. And so although this looks like Euler, it basically is, but we've already solved the hard part here with the midpoint method, and then all we're doing is we're just integrating whatever the midpoint method gives us. So that's all you need to do for these to solve for the second order differential equation. We can also do this with Runge-Kutta. So again, we set up our Runge-Kutta fourth order solver that we have K1 depends on V dot, and V dot depends on the velocity, the current velocity and the current position, and then we multiply that by dt. K2 is dt times V dot, and it's the current velocity plus this 1/2 of K1 and the current position, and K3 is dt times V dot of V at the current velocity plus 1/2 K2 and the current position. K4 is dt times V dot, so this derivative of the velocity at this current velocity plus K3 and the current position. And then the next velocity is the current velocity plus 1/6 of K1 plus 2K2 plus 2K3 plus K4, as we've already seen before. And so then how do we integrate this again? We do the exact same thing that we did with the midpoint rule, midpoint integration, which is that the next position step is just the current position step plus dt times the next velocity step. And that's all it is. It's not particularly difficult. And we can solve for the, so we put this velocity into an array for RK4 and the position into an array for for RK4 as well. And we didn't explicitly find the acceleration, although this v dot is the acceleration, we don't actually ever calculate it anywhere. So I just take the gradient of what we solved for with the velocity of the midpoint and velocity of RK4 to get the acceleration. Now we can also use this built-in solver, so we can import from this scientific package for Python, so scipy, that will be importing this ODE int, as we've done before. And so just as we saw in the previous example, we have we define this function as a function of y and t, and y is actually both the position and velocity, and so we have it in this order of position and derivative of position, and so then we have the derivatives as written as the derivative of the position and the derivative of the velocity, so v and -2 cv minus omega naught squared times x, and then we just have to return these derivatives. Just as we did before, we have y naught is an array of x naught and v naught, which we've already defined previously, and then we solve for this just by calling this solver that integrates this function using these initial conditions y naught, and we integrate over t. And so as I mentioned in the previous tutorial or previous lecture, our position of this built-in solver will be the 0th row of this p-soln array, and the velocity will be the first row of this p-soln array. Or is this column? I guess maybe this is column. I think I've been calling it row, but I guess it's actually column. Sorry about that. But yeah, so it's I guess it's the column of this array or this matrix. And then again, since we've calculated the velocity, we can calculate the acceleration just by taking the gradient. So this the numpy package has a gradient function that just takes the derivative. And so we just take the derivative of velocity to get the acceleration. And then we know the exact solution. So as you guys should have calculated on the midterm what the exact solution is going to be. So this is the position as a function of time. So we have, it's this v naught divided by the square root of omega naught squared minus c squared, so that drag coefficient squared, times this exponential damping factor, which is dependent on c, and then because we start with the initial position at 0, we don't have a cosine function, but we start with some velocity, so we have a sine function. And this oscillates with a slight modification to the natural frequency, which is the square root of omega naught squared minus c squared times t. So we can run this, and what do we get? We can see that the exact solution is in blue, and the midpoint in green, midpoint is in yellow, and RK4 is in green, and you can see that all these things exactly overlap with the built-in ODE and solver. We can show how much better the built-in solver is if we significantly decrease the number of steps, and so we can see that midpoint and RK4 are still pretty close to being right. They decay at about the right speed, but they're a little bit shifted in phase, just as we saw in the conservative case as well. But again, this built-in solver and the exact solution agree extremely well, even with these few number of points. So we can run this again. And I recommend that if you want to check your answer from your midterm, you can use this this code to do that. So you can change what your spring constant is, or you can change different parameters here to see which ones are underdamped, which ones are overdamped, and which ones are critically damped. And so obviously in this case, this oscillates back and forth many times, so this is underdamped. But you can now kind of check your answer that you derived for the midterm with this code to check your answer to see if it was right. And you can try seeing which case is better for underdamped, overdamped, or critically damped, for which would be best to survive in an earthquake. All right, so that's it for second order differential equation solvers. Next, I will go to, I will be discussing planetary motion, and I'll show you how to create animations for this orbital motion. All right, until then, stay safe and stay healthy.